Welcome to Maths with EJD. In this video, I continue with applications of eigenvalues and eigenvectors, and now the focus is on image compression. Okay, so eigenvalues and eigenvectors play a crucial role in image compression. Image compression, particularly in principal component analysis, which I talked about before, right? So this actually come together when it comes to image compression. Okay, let me write that in full. Particularly in particularly in principal component analysis. We saw principal component analysis in data science. Now, coming up in image compression, PCA, right? And another part of that is the singular value decomposition, singular value decomposition, SVD. Okay, SVD. Now, these methods reduce the dimensionality. We saw that happening actually when we looked at PCA for data science for reducing the data dimension. So these methods reduce the dimensionality of of image data while preserving essential features, while preserving essential features. So that way it will now improving storage efficiency. So you can have more space for storage, improving storage efficiency and transmission speed. Now, because image is lighter, now it's easy to transmit, transmission speed. Okay. Now let's look at an example. Example. So imagine if we want to use image compression, image compression using singular vector decomposition using SVD. Okay. Of course, we won't go into all the whole matrix number. I'll do a practical thing with an image. So to do this, right, step one, the first thing is you representing the image as a matrix. Represent the image as a matrix. Okay. So in that case now, a grayscale image can be represented as an M by N matrix A, an M by N matrix A, where each entry corresponds to a pixel intensity value, and that can range from 0 to 255 for a grayscale image, 0 to 255 for a pixel intensity value. So that's step one. So represent the matrix, represent the image as a matrix. Then in step two, so you now performing singular, performing SVD. Let me just say performing SVD, singular value decomposition, since we've seen that before. So using singular value decomposition, then we decompose the image matrix. We decompose the image matrix A as follows. So using SVD, right, we have A equals U, then this something like summation V transpose. So that's the kind of thing we have. Okay. So, and what does that actually mean? So here now, okay, we can say where U and V, U and V are orthogonal matrices. They're orthogonal matrices. I think those are matrices where the unit matrix is equal to the matrix times its transpose. So they are orthogonal matrices. U and V are orthogonal matrices containing eigenvectors, of AA transpose and A transpose A, like that. Those are what U and V are. This respectively, right? Respectively. Okay. Then, of course, this now is a diagonal matrix, is a diagonal matrix with singular values. It's a diagonal matrix with singular values. That is square roots, the square roots of eigenvalues, square roots of eigenvalues. And that is about step two. Then in step three, okay, we have the rank reduction for compression. Rank reduction for compression. Rank reduction for compression. So to compress the image, we approximate A. We approximate A using only the top K singular values, only the top K singular values. Okay. So the higher the singular value, the sharper the image would be. So here we have AK equals UK summation K. I don't know. I just call that summation. Maybe it's not necessarily summation. So that's what we have in that case now. So that K really matters because it determines how sharp the new image is going to be. And that is what happens in step three. In step four, which happens to be the final stage, in step four, we have the reconstruction, or rather reconstructing the image. Okay, so here, the compressed image is reconstructed, from AK. It's reconstructed from AK, that AK up there, significantly reducing storage size, significantly reducing storage size. So it's all about the K, like I said. So the higher the chosen K, the better, the higher the chosen K, the better the quality, with a larger file size. in as much as you want to compress an image, you also still want like a sharp image. So you have to balance between the value of the K and the sharpness you really want from the image. Okay. So I mean, I won't go too much into the whole matrix thing. I'll just do a practical. But before I go into that, so that grayscale representation which we talked about here, that A. So uh note the the image matrix can be something like it can be something like A equals, so you have 255, 255, 255, 255, and then you have 0, 0, 0, 0, and you have 0, 0, 0, 0, then 255, 255, 255, 255. So, I mean, that's what a grayscale image would look like. And then, of course, we can go into the whole SVD and everything, but I'm not going to worry about that. I'll just take you to the Python code that helps to implement this. Okay, let's look at the Python code that helps to implement the image compression. So what I'm going to do first is to show you the original image we're going to compress. So, of course, we are talking from the dimension of a grayscale image, but let me show you a color image. I call the image fitness space because it's a quote about fitness. So that's why I call it fitness space. So look at this now. So this is the image. So it's this brightly colored stuff with blue, black, white, and all of that. This is what it looks like. So this is the image I want to compress. So with that, now I go to the code. So this is the code right here, image compression code. So now you see we need everything we need from all the libraries and functions we need are declared from lines 1 to 4. Then in line 7, that's where we upload that fitness space. So as you can see, it's called fitness space and it's a JPEG folder. So if you click it, you see at the top it's JPEG. If it is JPG, so you make sure it's JPG. So back here now, so I have the fitness space dot JPEG. So, and that is our A. A is NP array of this image. Now, whatever this image is, that has been stored here as a matrix. Although you're not seeing the matrix, I've shown you what the possibility, what the matrix looks like. That this is the last thing we have here. So 255, 255, 00, and all that. So that's the kind of thing you have. So it has been stored here, and then we compute the singular vector decomposition, which is happening in line 11. And then this K actually will determine the quality of the picture. And then you have the AK, which is the decomposition into UK, so the diagonal matrix summation K, and then you have VK itself. U and VK, like we had, they are orthogonal matrices. Then all the rest are just to display. So the line 18 is just to plot original and compressed images side by side. So we want to see the original grayscale image, not the yellow and blue you saw now. So you want to see the original grayscale image side by side, and the whatever compression you have based on the value of K, and then you display the original image here, display the compressed image. Then we save the images, of course, so we can have that later. So um for now, we are taking K to be 5. So I'm going to store the picture as K equals 5, right? So we have the original image and the K equals 5 image. So if I click on this, it takes a bit of time and then it spews out the result. Spews out the result in a jiffy. Now see that. So you can see K equals 5. Now we have something blurry. So in as much as we want to compress, we still want the picture to be usable, right? So what I'm going to do is I'm going to copy that now. So you see, this is the grayscale of that thing, the original I showed you. So it's not the color thing because we are talking about grayscale, right? From what I described. So I bring it back here. So all I'm just going to do now is I want to increase the K to 50. You can see this K equals 5 is looking, I mean, it's of no use, right? In as much as we want to compress, we still want it to be useful. So I now save this as K50. So if I run this now, it takes a bit of time, then you're going to get a better quality. Yeah, so you see, it's better now. At least it's a bit legible, but then it can still be better than this, right? So I'll copy that again and change the K. So the value of the K is what determines what you have. So that's why you're taking the top K SVDs or something. So let me call this 100 now, okay? And then I save this as K100. Okay, so it's going to be a bit better now. Okay, so you can see although it's not as good as what you have here, but at least it's even better than what the first thing. So you can see it's clearer. So, but if you want, well, I mean, the purpose may be defeated, right? If the K is too high, because I'm sure you may not even be able to get up to 500. But let's say you now have like 200. Let's even say 200 and see what happens. From 200, I'll just jump to 500. But as it's going higher, it's getting close to the original grayscale image already. So look at this. So they are almost looking at like, although the original image is still a bit better. Okay, so finally, let me just do 500. So finally, let's do 500. So imagine we have this. So let me call this 500 now. So you see the two original and the compressed image would now look almost alike, which may not be necessary, right? Because you know, so now you see the quality is even better, though it's still not up to, it doesn't still match up to this. So the as you increase the K, things improve like that. So and that's how this has been today, talking about using eigenvalues and eigenvectors in image compression. And what the basic place where the whole thing is happening is where you have your image as a matrix, the grayscale of your image, you have it as a matrix, and then you compute it using the singular vector decomposition. That's where the whole eigenvalue and eigenvector thing is happening. So if you have not subscribed to this channel, if you have subscribed to this channel, thank you so much for that. If you have not subscribed, go ahead and do that and hit the notification bell so you can always get alerted each time a new video is released. Comment, let me know how helpful these videos are for you, and let me also know if there's a topic you'd like me to teach or a problem you'd like me to solve. I still have one more application, and it's going to be about a growth model. You talking about Leslie matrix and all that. So watch out for that. I guess there are many more I can do, but I'll be talking about that one lastly, right? Talking about applications of eigenvalues and eigenvectors in population models. Okay, so watch out for that. So like and share with others so that more people can have access to this great learning. Till I come your way again, keep doing much right. Bye.